section 15.7, Pascal's triangle. Oop, what? Pascal's triangle and the binomial theorem. The binomial expansion. Hmm. Uh-oh, that says something. Expansion. Let me just check what's happening there. I certainly hope that that didn't have an error. Okay, can you guys still hear me? Uh-oh, can't see. Okay, can't see. So let me just, but you can hear me, right? Okay, so let's do this. Okay, so now let's see. Hear you, but not see the screen. Okay, can you see the screen now? There. Okay, good. So I plugged in to my calculator and I got that your mortgage should be approximately $2,134.69 per month. Okay. And that really finishes off section 15.6. So let me go on to section 15.7. Pascal's triangle and the binomial expansion. So let's look at the binomial expansion. And so suppose I want to look at x plus y to the 0. Well, that's just 1. X plus y to the first. Well, that's just 1x plus 1y. X plus y squared. Well, that's x squared plus 2xy plus 1y squared. And let's look at x plus y cubed. That was 1x cubed plus 3x squared y plus 3xy squared plus y cubed. So let me put ones in front of each of these. And now let's look at what's called Pascal's triangle. And so Pascal's triangle is you start with a 1, then you just drop down the 1, drop down the 1. If I have something above it, then I just add. Well, 1 plus 1 is 2. Drop down the 1. Drop down the 1. If I have something above it, I add. 1 plus 2 is 3. 2 plus 1 is 3. Drop down the 1. Now, if you look, oops. If you look here, these coefficients are just, actually, let's see here, wait. Maybe I'll do it this way. These coefficients here Oh well, these coefficients, I guess I can't select them, not so easy. Maybe I'll just sort of highlight them in yellow. So these coefficients are just the same as Pascal's triangle. Notice 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So these are just the same as what's in Pascal's triangle. Now, actually let me write all the terms. I can write this as, oops, x to the 0, y to the 0. Well, that's just 1. X to the 1, y to the 0, y to the 1, x to the 0. Let's write the x to the 0 first. Y to the 1. X squared, y to the 0. X to the first, y to the first. Oh, I guess I need an x to the 0. Y squared. Cubed, then y to the 0, y to the first, x to the first, and let me write so that's a y cubed term here. Let me write the x to the 0. So if you notice, well, in the expansion, the coefficients are just the coefficients of Pascal's triangle. If I look here for the x's, well, they start out at whatever the power is, 1, then they keep going down, 1, 0, etc. Whereas for the y's, they start at 0 and keep going up. 0, 1, 2, 0, 1, 2, 3. Whereas for the x's, they go down, 3, 2, 1, 0. And notice that the sum, 3 plus 0, is 3. 2 plus 1, 3. 1 plus 2, 3. 0 plus 3, 3 is the same as this exponent. And that always works out. And so, to find that binomial expansion, I really just need to know something about Pascal's triangle. So, let me give you some facts about Pascal's triangle. But before I do that, let me give you some notation, the factorial notation. And so the factorial is denoted by this exclamation point. And so I'll define 0 factorial as 1. I'll define n factorial recursively as n times n minus 1 factorial. This is for n being some natural number. So therefore, I can define any sort of factorial. So note, if I wanted to figure out, let's say, 4 factorial, it would be 4 times 3 factorial. So that's 4 times 3 factorial. But 3 factorial is 3 times 3 minus 1 factorial. And so this is 4 times 3 times 2 factorial. But 2 factorial is 2 times 2 minus 1 factorial. So it's 4 times 3 times 2 times 1 factorial. But 1 factorial is just 1 times 0 factorial, which is 1. And so 4 factorial is just 4 times 3 times 2 times 1. So to figure out a factorial, you just multiply all those factors together. And so 4 factorial in this case is going to be 24. Now, on your calculator, there should be an X to the Y button. So this X to the factorial button. There should be some on your calculator, or, oh, let's see. Actually, I have a TI-83. If you had a TI-83, I'll show you that because that's actually hidden. So on most calculators, it's obvious where the factorial is. And so why don't you calculate? Let's see if I can do this for it. Get rid of that. And so why don't you calculate 8 factorial? Do that on your calculator. So on my calculator, I will do 8. And then unfortunately, it's under math, PRB, and there it is, the fourth one down. Oops. I said a whole bunch of, it's more 8s than I thought. 8, go to math, PRB, it's the fourth one down. Okay, he's doing a lot of weird things. Why are you doing all this? Stop. 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 It's the fourth one. Good. And so it comes out to 40,320. Okay. And that's your answer. And so you should be able to do that on your calculator also. Okay. The binomial coefficient. The binomial coefficient is sometimes denoted by the following. Now, it's an N and an R floating above each other with the parentheses around it. So it is not N divided by R parentheses. That's not what I'm writing. I am not putting a line there. So it is not N over R. It is really, didn't forget the line. It's just an N floating above an R in a parentheses. Or other people write it as NCR, and that's, especially if you're in a statistics class, that's how they would write it, NCR. It is defined as the following: N factorial over R factorial, N minus R factorial. And that's your definition. Okay. And so, suppose I wanted to calculate 12C4. I would do 12 factorial over 4 factorial times 12 minus 4 factorial. So this is 12 factorial over 4 factorial times 8 factorial. But let me write it the other way around. Let's write it as 8 factorial times 4 factorial. And so this would equal 12 times 11, 10, 9, 8, 7, 6. Oh, I see that. No, just keep it the other way I wrote it. Times 5, 4, 3, 2, 1 over 4 factorial 4, 3, 2, 1. 8 factorial, 8, 7, 6, 5, 4, 3, 2, 1. Notice that 1's cancel, 2's, 3, 4, 6, 7, 8. Those all cancel. And so, there are other things that cancel. 12 divided by 12 cancels. 10 divided by 2 is 5. And so it's just 45 times 11. 45 times 11. And so 495. Now, on a calculator, you would just calculate 12C4. Okay, so on a calculator, you would look for the NCR button and you'd calculate it. So 12C4, so let's do that. And so I would do 12C, oops, sorry about that. So let's do 12C, that's the third one, 4. And notice you get 495, same answer. Okay. Good. Let's calculate, let's say 3C2 on Pascal's triangle. So, to do that, I would do the following. And so, I would say, well, when I go, the first thing is to figure out n. And so, n, well, you start counting at 0. So 0, 1, 2, 3. And so, it's going to be this row. Now let's figure out the column. I said 3C2. So you start counting at 0. That'll give me my R. And so 0, 1, 2. So this number here is 3C2 is 3. Because that is the number in the third, well, the row calculated by 3. It's really the fourth row. And the column calculated by the 2, which is the third column. So fourth row, third column gives me 3. You got to start counting at 0. So if your number is relatively small, you can just do Pascal's triangle and from there figure out what the binomial coefficient is. And so let me give you the binomial theorem. Well, let me give you the binomial theorem. Which says that x plus y to the n is equal to the sum k equaling 0 to n of nck x to the n minus k y to the k. And let me give you some additional notation. And so if you recall, well, when calculating this, like these the n minus r's sort of just canceled out. And so let me use as a notation nck is equal to n minus 1, n minus 2, all the way to n minus k plus 1, all over k factorial. Okay. And this is actually true for any real number k, for n being any real number, and k being some natural number, some whole number. Okay. So then I have the following binomial theorem. And maybe just to make my life easy, I'll assume that x is 1. And so let's write this as 1 plus r to the n. For any n is just the sum, k equaling 0 to infinity, of nck, where n is this power, times r to the k. And that's your binomial expansion. And this is true for any number n. So n could be like, pi or something. So this is, n doesn't necessarily have to be a natural number for n being some real number. Okay. As long as I make that notation. Notice that if n is a natural number, then eventually these NCKs become 0 at the end. So it's really a finite expansion. So let me do some examples. Let's say on page 692, let me do problem number 2, r plus s cubed. And so in this case, I want to use Pascal's triangle to calculate this. And so in exercises 1 through 8, use Pascal's triangle to expand the binomial. So we want to go up to x cubed. So let's do the Pascal's triangle. So I'll start with 1, drop down the 1, drop down 1, add, drop down the 1, add, drop down the 1. So that's 0, 1, 2, 3. And so these are my coefficients. And so it is 1. Well, let me write them out. Yeah, so this will be 1 r cubed s to the 0 plus 3 r squared s to the 1 plus 3 r to the 1 s squared plus 1 r to the 0 s cubed. Putting in for the, actually maybe I'll write it out. Let me write it out first, and then I'll put in the ones. This is the sum, k equaling 0 to 3 of nck r to the n minus k s to the k, the binomial expansion. And so this is 3, and of course n is 3. 3 is C0, r cubed, s to the 0, plus 3C1, r to the second, s to the 1, plus 3C2, r to the first, s squared, plus 3C3, r to the 0, s to the third. And so 3C0, as I said, that was 1. And s to the 0 is 1. 3C1 was 3, r squared s. 3C2 again was 3, r to the first s squared. 3C3 is 1, r to the 0 is 1, s cubed. And so we get r cubed plus 3r squared s plus 3rs squared plus r plus s cubed. And that is our formula using Pascal's triangle. Let me do problem number 7. AB minus 2C to the fifth. So, by Pascal's triangle, well, by the binomial expansion, this is sum k equaling 0 to 5 of 5ck AB to the 5 minus k, negative 2c to the k. And so this is 5c0 AB to the fifth, negative 2c to the 0, plus, oh, and by the way, the assumption here in the binomial theorem is that we assume that 0 to the 0 is equal to 0 or 1 to make the formula work. So just make it so that, you know, if some of the if some of the variables are 0, it works out so the formula works. So that's sort of a loose sort of understanding that, you know, rather than doing all these subcases of when things are 0, when things are not 0, we just sort of say, well, the formula works even when it's 0, as long as you make the appropriate choices of what 0 to the 0 means. And you can do that because 0 to 0 can mean anything. So we'll just arbitrarily make it equal zeros and ones wherever we need to have it either equal to 0 or 1 so that the formula works. Okay, so that's sort of the implicit assumption that we're making in these expansions. 5c1, ab to the 4, negative 2c to the 1, plus 5c2, ab to the 3, negative 2c to the 2, plus 5c1, ab to the 4, negative 2c to the 1, plus 5c0, ab to the 5, negative 2c to the 0. So first off, notice, uh-oh, I hope I don't do anything. Okay, can you still see me? Join left, join left, join left. Can you guys still see me? Yes. Okay, assume. Can you guys still hear me? Okay. Hello, hello. Okay, so let's keep doing this. So notice that, how do I figure out the 5? I just do 5 minus 0 is 5. This 0 is the same as that 0. 5 minus 1 is 4. This 1 is the same as that 1. 5 minus 2 is 3. And this 2 is the same as that 2. 5 minus 1 is 4. This 1 is the same as that 1. So 0 is the same as this 0. 5 minus 0 is 5. Okay, okay, good, good, good. Yes. Okay, just checking. Okay, so this is equal to, so now what I have to do is Pascal's triangle. So I've got to do 5 of them. So let's do 1, 2, 3, 4, 5. Okay, so there it is. And so it is 1 AB to the 5th, negative 2C to the 0 is 1, plus 5 AB to the 4th, plus 5C2, which is 10, A to the 3rd, B to the 3rd. Negative 2 squared is 4. C squared is C squared. Plus 5C1 was 5. A to the 4. What the heck? 4, 3, 2, 1. 0, 1, 2, 3. How did I skip? 0, 1, 2, 3, 4, 5. Okay, so that is 5 minus 3 is 2. The 4 goes here. 5 minus 1 is 5 minus 4 is 1. 5 minus 5 is 0, and the 5 goes here. Okay, so now that gives me all of them. Okay, so 3. That was correct. And then squared, squared. Negative 2 cubed is negative 8c cubed. And that's a 5, 5. Oh, that's 3. 1, 2, 0, 1, 2, 3. That's a 10. Okay, that's a 10. Plus the fourth one is, that's a fifth. 2, 4, 5 is 5. AB to the first, so AB. Negative 2 to the fourth is 16. C to the fourth. Plus 5, C5 is 1. AB to the 0 is 1. Negative 2 to the fifth is negative 32. C to the fifth. Okay, so now A to the fifth, B to the fifth. 2 times 5 is 10. Why are you doing this? A, B, C to the fourth. No, I'm looking at the wrong thing now. A to the fourth. B to the fourth C. Plus 10 times 4 is 40. A cubed, B cubed, C squared. Plus 10 times negative 8. Negative 80. A squared, B squared, C cubed. Plus 5 times 16, 80. A, B, C to the fourth. Minus 32, C to the fifth. So let's see. And so 0, 1, 2, 3, 4, 5. Good. 5, 4, 3, 2, 1, 0. Good. And that is your answer. Okay, so let me do problem number 9. 2x plus 3y to the 10. Oh, I guess I should note here. Let me just put a note. For statistics, they write it backwards. So mathematics, we write the binomial. So x plus y to the n is equal to, so in mathematics, we write sum k equaling 0 to n of nck x to the n minus k y to the k. In statistics, they just write it backwards, and so they do the sum r equaling 0 to n of ncr, and they write it as x to the r y to the n minus r. So they just write it rather than going left to right, they go right to left in the expansion. But they're obviously the same terms. It's just that they write them in the opposite direction that we would write them, that mathematicians would write them. Okay, let me do problem number 9. 2x plus 3y to the power 10. No, he can't. Uh-oh. Professor, you're going too fast. All right, stop. Okay. Oh, I can't hear people. I wonder why. Okay, so I wonder why I can't hear you. Can you guys hear me? Can you hear me? Yes. Okay, so um, let us let me scroll back for a second then. I think some people couldn't hear or couldn't. I was going a little bit too fast with all the numbers. Okay, so probably, is this a good place? Is this a good place? Yes. Okay. And then I'll go back down. Yeah, there are a lot of numbers there and to look at. Let me scroll down slightly. Just to be sure that people have gotten all that. It's hot, it's hot. It's hot. Let me scroll a little bit down, a little bit more. It's very hot. I don't have a blanket. Oh no. I don't have Okay, let me scroll down. Is the class going to end? Yes, when we get through with this section. Okay. Okay, so let's do this. So this is equal to, well, let's do the binomial expansion. So this is the sum, k equaling 0 to n, of nck x, or the first coefficient, to the n minus k, second coefficient to the k. Okay, and so it says, in exercises 9 through 12, use the binomial theorem to write out the first, just 4 terms of the expansion. So let's write out the first 4 terms. So 10, see 0, 2x to the 10, 3y to the 0, plus 10c1, 2x to the 9, 3y to the 1, plus nc2, 2x to the 8, 3y to the 2, plus nc3, 2x to the 7, 10 minus 3 is 7, 3y to the third. And so this is plus a whole bunch of other terms. Okay, well, 10c0 is just 1, so plug that into your calculator. That's 1. 2 to the 10 is 1,024 times x to the 10. And 3y to the 0 is just 1. 10c1 is 10. 2 to the 9th is what? 512. X to the 9 times 3y plus 10c 2, which is 45, times 2 to the 8th, which is what, 256, x to the 8. 3 squared is 9, y squared. Hopefully people are checking these because I'm just sort of doing it in my head. Plus 10c3, uh, 128 x to the 7 and 27y cubed. Let me just check. Let's see. This would be 90, 15 times 735, and 70 is 105. Okay, so I think that's correct. Let me actually do these on a calculator. So let me check some of these values on a calculator. Okay. Oh, 120. Oh, I did that wrong. It's 120. How did I do that? 10 times 9. Oh, times 8. Times 8. 80 plus 40. Yes, times 8. Okay. And then that's etc. And so this is equal to 1024 x to the 10 plus multiply the 512 times 10 times 30, 15,360. 15,360 x to the 9y plus multiply the 45 times the 256 times the 9, 103,680 x to the 8y squared. Multiply the 120 times the 128 times the 27. And so 414,000, 414, 720 x to the 7, y to the third, plus etc. And those are the first 1, 2, 3, 4 terms. Notice that if you look at these, well, notice that the subscript, since you start at 0, is actually, so the fourth term is actually 10C3 rather than 10C4 because you're starting out at counting at 0. Okay. So let's say, problem number 15. Does everyone got this? When are you going to be able to watch this? Once I'm done, it usually takes about 2 hours or something after I've completed this to be able to watch the recording. For me to be able to actually download it to EducoSoft, it won't be till tomorrow morning because it takes about that long to process everything. Maybe a little less depending on how fast YouTube is on uploading things. Okay, so let me do problem number 15, which says x squared plus 2 to the 11th, and I want to find the nth term. And so let's look at the 10th term. This is just going to equal the sum, k equaling 0 to 11, of 11ck x squared to the power 11 minus k, 2 to the k. And so the 10th term occurs when k is 9. So if I look at this formula and I just plug in 9, so it's going to equal 11c9 x squared to the power 11 minus 9 is 2. 2 to the power, well, I just bring up the 9. So let's calculate this. So let's calculate 11 C9, which I think is 55. X squared squared is x to the 4th. 2 to the 9th should be, what, 512? Let me plug all this into the calculator just to be sure that I did my calculations correctly. And so this is 11 C9 is 55, correct. 2 to the power 9 is 512. And so the 10th term is 228,160 x to the fourth. And that is the 9th term in this series, in this expansion. Okay, let me do problem number 17. A squared minus 2b cubed to the 10th. Let's find the middle term. So, if I look here at Pascal's triangle, or the expansion, so notice if n was 4, then there would be 1, 2, 3, 4, 5 terms, and the middle term would be the third one. So that's 5 plus 1 is 6 divided by 2 is 3. And so that's the, well, that's the third term. Or if I just do 4 divided by 2 is 2, so that would be the case when k is equal to 2. If I looked at the sixth one, right, there would be, well, we'd have to do one more out. And so that would be 1, 6, 15, 20, 15, 6, 1. And so the 6 divided by 6, oh, I see, there's not a, that's a 20. It's 0, 1, 2, 3. So 6 divided by 2 is 3. So it would be when k is equal to 3. And so to find the middle term, that implies that, well, the middle term is when k is equal to n over 2. And that gives me the middle term, so long as I'm starting to count when k is 0. So I'm counting when k is 0. And so the middle term equals 10 divided by 2 is 5. So that'll be the fifth term. So it's really asking for the fifth for the case where k is 5. It's actually the sixth term, but and so figure out when k is 5. And so the binomial expansion is k equaling 0 to 10 of 10ck a squared to the power 10 minus k. Let me move this guy over a little bit. Negative 2b cubed to the power k. And I want to figure out when k is 5. And so this would be 10c5 a squared to the power 10 minus 5, which is 5, negative 2b cubed to the power, well, 5, because the subscript is 5. The lower number is 5. And so 10c5, well, let's calculate that. Is 252. A squared to the power 5 is a to the 10. Negative 2 cubed is negative 32. B cubed to the 5 is b to the 15. And so Negative 32 times 252 is negative 8,064, a to the 10, b to the 15. Let me do problem number 21. X to the 4 minus 3 over x squared to the 6. And I want to find the constant term. Well, what do we mean by constant term? A constant term is a term that only consists of numbers. So what that means here is that I want a term with x to the 0 as a power. Okay? And so let's do that. And so if I look at my expansion, it's just equal to the sum k equaling 0 to, in this case, 6 of 6ck x to the 4th to the 6 minus k negative 3 over x squared to the k. Well, so each of these terms look something like that. And so I want some constant. I want to find k so that this term here is some number times x to the 0. So let's first figure out what the k is. So I don't really worry about the constant yet. Then I'll figure out what the constant is. So let me get rid of all the constants. And so anything that doesn't involve x. So this is just x to the 4th, 6 minus k. The negative 3, well, that's a constant, so it's 1 over x squared to the k. I want that to equal x to the 0. So I've just gotten rid of all the extraneous stuff, so I can figure out just what k is. So this is x to the power. Multiply the 4 times the 6 minus k. That's 24 minus 4k. X to the 1 over x squared to the k as well. X squared, 1 over x squared is the same as x to the negative 2 times k is negative 2k. And so I get, by laws of exponents, I have the same base, so I'll add exponents. So this is x to the power 24 minus 6k should equal x to the 0. Since the exponential function is 1 to 1, then the only way that these can be 0 is if the exponents are the same. And so 24 minus 6k is 0. Add 6k to both sides. And so I have that 24 equals 6k. And so divide both sides of my equation by 6. So k equals 4. So to find the constant term, I just want to plug in 4 into this expansion here. And so it looks like 6c4 x to the 4 to the 6 minus 4 negative 3 over x squared to the fourth. So let's simplify that. 6c4 should be 15. Let me check that. Okay. X to the fourth squared. 6 minus 4 is 2. Negative 3 to the fourth is 81. X squared to the fourth is x to the eighth. And maybe I'll write that x to the eighth also. The x to the eighths cancel. And so you just get 81 times 15, 1,215. And so if I look at this expansion, one of the terms in this binomial expansion is just the pure number 1,215. Okay, good. Any questions about that? Can scroll up again. Okay. Is that good? A little up, a little more up. Okay. How about that? Yes. Okay, good, good. Let me go down a little bit more. Let me scroll down a little bit more. Let me scroll down a little bit more. Oh, then that's it. Okay, so let's recall Pascal's triangle. And so let's construct it again. So you start with 1, then you add what's above. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 1 is 3. Drop down to 1. 3 plus 1 is 4. 3 plus 3 is 6. 3 plus 1, 4. Drop down to 1. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Drop down to 1. 1 plus 5, 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1, 6. Drop down to 1. Okay. So let me give you some properties of Pascal's triangle. Properties of these binomial coefficients. So binomial coefficients. And so the first is that NC0 is always equal to 1. And so this says here that all these numbers are always equal to 1. Okay. And so let's show that. So let's recall also that NCK is equal to n factorial over k factorial n minus k factorial. Okay. And so if I plug in 0, I get, oops, why did I write it that way? NC0 is equal to 1. Well, let's show that. Well, NC0 is just equal to n factorial over 0 factorial n minus 0 factorial, which is n factorial over 0 factorial n factorial. The n factorials cancel. So you get 1 over 0 factorial, but 0 factorial is 1. And that's what you wanted to show. So also we call that 0 factorial is 1. And n factorial is n times n minus 1 factorial. 2. NCN is 1. So that says, and if I look at the right-hand side, all these terms are equal to 1. So let's show that. NCN is equal to n factorial over n factorial, n minus n factorial. Just plugging in for k in this formula here, replacing k by n. Well, again, n minus n is just 0. The n factorials cancel. 0 factorial is 1. 1 divided by 1 is 1. So you're done. Let me do the third. Property. NC1 is n. And so, if I look at these are always just n. And so that's 1, 2, n is 1, 2, 3, 4, 5, and 6, etc. in this case. And so I have that nc1 is equal to n factorial over 1 factorial n minus 1 factorial. But again, n factorial is just n times n minus 1 factorial. 1 factorial is just 1. The n minus 1 factorials cancel. N divided by 1 is just n. And so I'm done. Any questions about that? Okay. 4. NCR is equal to NC n minus R. Well, maybe I'll use a K because my R's look like N's. And this is symmetry. And so this says that if you look at this half of Pascal's triangle, it's the same as the other half. They're just mirror images of each other. And so there's this symmetry where if you look at each side, they have the same numbers, right? 3, 1, 3, 1, 4, 1, 4, 1, 10, 5, 1, 10, 5, 1, 15, 6, 1, 15, 6, 1, etc. So there's this symmetry. So let's show this. And so I have that n c n minus k is just n factorial over n minus k factorial times n minus k factorial. So this is equal to n factorial over n minus k factorial. Let me change all the signs. And so I have a minus out here. So I can change all the signs inside the parentheses. So it's n minus n plus k factorial. So the n's cancel. And you just get n factorial over n minus k factorial times k factorial. Now let me just interchange the order in the denominator. And so this is just equal to n factorial over k factorial n minus k factorial. But by definition, this is just nck. And that's what you wanted to prove. Any questions about that? Okay. Next, nck minus 1 plus nck is n plus 1 ck. And so the way that you determine, let's use green, I guess. The way that you determine any value is you add up the two before it. So if you add up these two, you get the next one. And that's what they're telling you here. Okay, so let's do this. N over k minus nck minus 1 plus nck is equal to n factorial over k minus 1 factorial times n minus k minus 1 factorial. Just using the definition of a factorial of the binomial coefficient plus n factorial over k factorial. Where did that come up? Probably here. Times n minus k factorial. So this is equal to k minus 1 factorial. This is just n minus k plus 1, just changing all the signs inside the parentheses. This is n factorial plus n factorial. This is k factorial. This is n minus k factorial. So now I want a common denominator. In order to add fractions, I need a common denominator. The common denominator is k factorial, n plus 1 minus k factorial. And actually, let me write it like this. It'll be nicer. And so here, what I'm missing is k. I have the n minus k plus 1 factorial, which is the same as n plus 1 minus k factorial. So what I need here is to multiply and divide by k. Here, I'm missing the n plus 1 minus k. I'm missing that term. And so this becomes, well, n factorial times k, so n factorial times k. This becomes, well, let's multiply the n factorial inside the parentheses. And so this is n times n factorial times n plus 1 is just n plus 1 factorial minus n factorial times k. So let's write this all over common denominator, which is k factorial n plus 1 minus k factorial. So I have an n factorial times k plus, well, n factorial times n plus 1 is n plus 1 factorial. The n factorial k's cancel. So I just get n plus 1 factorial over k factorial n plus 1 minus k factorial. But this is, by definition, n plus 1 over k, n plus 1 ck, the binomial coefficient. And so you are done. And so here, so that, so all you needed to do is really just find a common denominator. Once you found the common denominator, then everything falls out quickly. Okay, so let's do the next property, which I think is 6. The sum of all of your binomial coefficients is just 2 to the power n. And so if I look at all of these, well, so this is to the 0. If I add 1 plus 1, I get 2. One plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. 1 plus 4 plus 6 plus 4 plus 1, that's 10, 14, 16. To the 5th, that should be 32. And so that gives me 1532. Good. To the 6th should be 64. And so that's 20, 50, 70, 50, 62, 63, 64. Good. So if you add up each of these rows, they just give you 2 to the power. Well, let's show this. 2 to the n. Well, 1 plus 1 is 2. And so let's do the binomial expansion. So the binomial expansion is sum k equal 1 to n of nck, 1 to the n minus k, 1 to the k. But 1 to the k, 1 to the power n minus k is just 1. 1 to the k is just 1. And so 1 times nck is just nck. And that's what you wanted to show. So you just expand 1 plus 1, since 2 is equal to 1 plus 1. Let's do some of the absorption properties. R, NCR, maybe I should write the R here. R, NCR is equal to N minus 1, CR minus 1. Okay. So let's show that. Well, R times NCR. NCR is just equal to N factorial over R factorial, N minus R factorial. Next, R factorial is just R times R minus 1 factorial. By definition of factorial, the R's cancel. So this is just equal to N factorial which I can write as N times N minus 1 factorial over R minus 1 factorial N minus R factorial. Which is equal to let's write the n out in front. So it's n minus 1 factorial over r minus 1 factorial. Note that n minus r is the same as n minus 1 minus r minus 1, which is, well, by definition, just substituting for n minus 1, for r minus 1. This is n minus 1, cr minus 1. And you are done. Note, I guess, that n minus 1 minus r minus 1, change all the signs inside the parentheses, is equal to n minus r. So that's why I replaced n minus r by n minus 1 minus r minus 1. Obviously, differences are translation invariant. Okay. Let me do property number 8. R times r minus 1 times NCR is equal to n minus 1, n minus 2, CR minus 2. Okay. So let me do that. It will be very similar to the previous proof. And so r minus 1, NCR is r minus 1. NCR, by definition, is n factorial over r factorial n minus r factorial. Oh, I guess I should be using k's here, but it doesn't matter. Hopefully you can tell the difference between my r's and k's. So this is equal to r minus 1 in factorial. I'll write as n minus 1 times n minus 2 factorial. R factorial I'll write as r minus 1, r minus 2 factorial. The r minus 1's cancel. Let me bring the n minus 1 out in front. What remains is n minus 2 factorial over r minus 2 factorial times, well, instead of writing n minus r, remember that that differences are translation invariant. So just like I subtracted 1 from both of the r's and n's and got the same difference, I'll subtract 2. So, and the same, obviously, calculation works. And so this is n minus 2 minus r minus 2 factorial. So that's n minus 2 minus the quantity r minus 2 is certainly the same as n minus r. But this, well, if I look here and I just plug in, substitute for n minus 2, for r minus 2, this is just n minus 2 cr minus 2. And that's what I wanted to show. And so I can show this in general. Let me see. So a notation for permutation and combination. So combination, so this is, I guess, notation. Permutation. The number of permutations. P, let's say NCR is just n factorial over n minus r factorial. Let me use k's rather than r's so that I'm sure that you don't confuse my n's and my r's. So p npk is n factorial over n minus k factorial. And for combinations, nck is n factorial over k factorial n minus k factorial. Okay. So I have the following relationship for my, this is 9, for my absorption. RPK in CR is the same as NPK n minus K C R minus K. Okay, so let's prove this. And it's basically going to work the same way that we did it previously. It's just that now I want something slightly different, but it should work sort of the same. And so, actually I've never proved it the other way around, so maybe I'll do it that way. See if it works out any easier. NPK times n minus kc r minus k. Okay, well, let's see what this is equal to. NPK, by definition, is n factorial over n minus k factorial. The n minus kc r minus k is n minus k factorial over r minus k factorial times, well, the difference of these. And so it would be n minus k minus r minus k factorial. Okay. And so this is equal to n factorial over, well, the n minus k factorials cancel. And let's distribute the minus sign. So this is n minus k minus r plus k factorial. The k's cancel. And so this is equal to n factorial over r minus k factorial times n minus r factorial. Okay, well, that's good. So I want npk, so that's n factorial over I want n minus k factorial. So let's write this as, well, let's multiply and divide by n minus k factorial. So let's multiply and divide by n minus k factorial. And, well, the bottom is the r minus k factorial, and the n minus r factorial. So we're almost done. The first term is correct. So this is n factorial over n minus k factorial. The second term is almost correct, so it's n minus k factorial over r minus k factorial. But now I want to write this n minus r as the difference of n minus k minus r minus k. And well, that is certainly a true statement because, well, actually, I should have kept it in that form. Oh, you stupid. I'm looking at the wrong side. Oh, I hate you. 1 second. I'm sorry. I'm going I decided to go the other direction. And so this is equal to, I'm sorry. Erase, erase, erase. I wanted the other direction. Of course they're equal. They're the same thing. So I got this. So I want to write it as r. So that term is correct. Okay, so I want to write this as r factorial over r. So I want to write this as, let's multiply and divide by r factorial. So this is equal to r factorial times n factorial over r minus k factorial. And I have here an r factorial n minus r factorial. And so this first grouping is just RPK. The second grouping is NCR. And that's what I wanted to show. It's about the same amount of work going either way. Okay, 10. Let me scroll up for a second to be sure everyone has that. Oh no. Approximate time is probably about 10 minutes or so, or 15 minutes. Just one or two more things to do, then I'm done. Two more. Okay. Number 10. Sum I equaling 0 to k of ACI times BCK minus I is equal to A plus B CK. So the idea is that 1 plus x to the A times 1 plus x to the B is equal to 1 plus x to the a plus b. And I'm going to do this using the binomial expansion. I guess I'll prove the binomial expansion in the very last step, even though we've used it in two places. And so let's show what each of these are equal to. Well, 1 plus x to the a by the binomial expansion is just I equaling 0 to a I equaling 0 to a of ACI 1 to the a minus I x to the I by the binomial expansion. So this is equal to the sum I equaling 0 to a of ACI x to the I. Let's do 1 plus x to the b. That's the sum j equaling 0 to b of b cj 1 to the b minus j x to the j. And so this is the sum j equals 0 to b bcj 1 to any power is 1 x to the j, again with that notation. So this is 1 plus x to the a 1 plus x to the b is the product of these, and so this is the same as the sum I equaling 0 a ACI x to the I sum j equaling 0 to b of bcj x to the j which is equal to, so you can multiply these out by the distributive property, and so this is the sum I equaling 0 to a sum j equaling 0 to b of ACI BCJ of x to the I times x to the j. And so that's same as x to the I plus j. Now let k equal I plus j. So then this is equal to sum k equaling 0 to a plus b, the sum I equaling 0 I'll use I to k of a ci bcj, so j is k minus I, x to the I plus j, which is just k. Good. Also, so let me just sort of note this term here. And so these are the coefficients really of x to the k. We also have we can expand 1 plus x to the a plus b. Okay, so we'll do that. So 1 plus x to a plus b by the binomial theorem is the sum k equaling 0 to a plus b of a plus b ck x to the 1 to the a plus b minus k x to the k, which is equal to k equaling 0 to a plus b x to the k. Since 1 to any power is just 1. But I noticed that, oops, that these are the coefficients of x to the k. So therefore, since the coefficients are the same, I've shown that the sum I equaling 0 to k, ACI BCK minus I is the same as A plus B CK. And that's what you wanted to show. Okay. Just one short thing left is to show the binomial theorem. Let me leave that up for a second. And then we'll show the binomial theorem. Okay, so the following notation in the following theorem. The binomial theorem. Following binomial theorem, I guess I'll say. I will let 0 to the power 0 equals 0, or 0 to the power 0 equal 1 in the appropriate places. So that the theorem holds. Okay, so these are sort of the trivial cases. So I'll assume that I can prove this in the case that each of these terms are not 0. So let me have the binomial theorem. Which I guess is the 11th one. Was that 11 or 12? No, I just forgot. This was what, 10? Yeah, so this is the 11th one. And so 1 plus y to the n is the sum k equaling 0 to n of nck x to the n minus k, y to the k. So let's do the proof. Again, I'll assume x is not 0 and y is not 0. Just because we've made the assumption that we're going to make, the 0 to the 0 whatever it needs to be so that this theorem will work. So either 0 or 1 so that the theorem works. So let's prove this using mathematical induction. And so the initial case. Well, let's assume that n is 0. X plus y to the 0. Well, anything to the 0 is 1. Again, I've made the appropriate assumption that, I guess I assumed here, any non-zero number to the power 0 is 1. Next, let's look at the expansion. The sum, k equaling 0 to 0, of 0 ck x to the 0 minus k y to the k. And so plug in 0, that's the only term here, so it's 0c0 x to the 0 y to the 0. Again, 0c0 is 1, x to the 0 is 1, y to the 0 is 1. So therefore, I've shown that x plus y to the n is equal to the sum k equaling 0 to n of nck x to the n minus k y to the k, that this holds when n is equal to 0. Okay, so let's now do the induction step. Notice here that the principle of mathematical induction holds whenever we have the initial case. The initial case doesn't have to be 1. It's whatever is initial in this particular theorem. In this case, the initial one is 0, and it has to have successors, which in this case are the next whole number. So let's do the induction step. And so for the induction step, I want to assume that x plus y to the n is equal to the sum k equaling 0 to n of nck x to the power n minus k, y to the power k, that this is true. Then x plus y, the n plus 1, I want to show that that's equal to this formula where I replace n by n plus 1. Well, this is equal to x plus y times x plus y to the n, which is x plus y. And, well, I've assumed that x plus y to the n is just the sum k equaling 0 to n of nck x to the n minus k y to the k. And so let's multiply the x and y inside the parentheses. So let's multiply these inside the summation. And so this is equal to sum k equaling 0 to n of, well, let's multiply by x, so that's n ck x to the power n minus 1 n minus k plus 1 plus, well, let's multiply the y, the sum k equaling 0 to n of nck x to the n minus k y to the k plus 1. So I'm adding one more. Okay. And so let me write out the very first term of this expand out the first term for this first summation. And so plugging in k equals 0, I get nc0. Where's the y? There was a y that was missing. Plugging in 0, I get x to the n plus 1, y to the 0, plus this other expansion, k equaling 0 to the n, k equaling 1. I already did the 0. I wrote it out. K equaling 1 to n of nck x to the, let's write the n and the 1 next to each other, n plus 1 minus k, y to the k, plus, plus this next term. Let's expand it and write out the last term. So let's write out the first n of these. And so the very last one is found by replacing n, k by n. And so this is equal to nc0 is just 1, x to the n plus 1, y to the 0, plus this sum here, sum k equaling 1 to n nck x to the n plus 1 minus k y to the k, plus, now I'm going to let r equal k plus 1. For this next term. So this is the sum, r equaling, let's see, k is 1, so that's 1, k is 1, so that would be n. N minus 1 plus 1 is just n, of nc, well, I'm replacing k by r minus 1, so that's r minus 1, x to the power, n minus k, but k is r minus 1, plus the last term, which again was 1, x to the 0, which is 1, y to the n plus 1. So this is equal to x to the power n plus 1, y to the 0. And I'm going to probably write this as 1, but I can write 1 kind of strange. I can write it as n plus 1 cn plus 1, which is just 1, plus, now this is the sum. Why did I forget the last term, which is k plus 1, which is r? Okay, plus the sum k equaling 1 to n. Notice that the y to the, notice that r is a dummy index, so I can think of it as being the same as k. Notice k goes from 1 to n, so does r, goes from 1 to n. So we can think of these as being the same. The y to the k and the y to the r, those are obviously the same term. It's just that, remember k is the same as r. And then the n minus r minus 1, well, that's the same as the n plus 1. That's n plus 1 minus r, which is the same as n plus 1 minus k. So this is the same as nk plus nk minus 1 x to the n plus 1 minus k y to the k plus the very last term. Oh, I see. I did want to write it as 0, 0. I wanted to write this as 0, 0. And then this 1 here, I'll write that one as n plus 1 cn plus 1. This is x to the 0, y to the n plus 1. Now notice, so 0, 0, x to the n plus 1, y to the 0, k equaling 1 to n. We just proved this, that nck plus nck minus 1 is just n plus 1 ck. That was, I think, property 4 above. X to the n plus 1 minus k y to the k plus the last term, n plus 1 cn plus 1 x to the 0 y to the n plus 1. But this is just the sum, k equaling 0 to n plus 1 of n plus 1 ck x to the n plus 1 minus k y to the k. Notice that this first term is just the first term in this expansion. This last term is the last term in this expansion. And that's what I wanted to show. And so, therefore, so I've shown the induction step works. Therefore, by the principle of mathematical induction, for any n being a natural number, actually a whole number, we have that x plus y to the n equals the sum k equaling 0 to n of nck x to the n minus k y to the k. And so I am done. And so that finishes off. Oh, wow. And so that finishes off section 15.7, which finishes off the book. And so, what? And so, that's it. And so, if you write up these lecture notes, get them to me by Monday, before Monday at midnight, then you will get 5 points extra credit on the Math 115 final and on the Math 125 final. Any questions? Do we have class on Tuesday? No, we're done. We're done with the course. There are final exams on Wednesday and Thursday. And so, yeah, the course is done. This was the very last topic in this course. 5 credits. Yeah, so 5 extra credit points added to the Math 115, and 5 up to. I'll say up to. Depends on how thorough your lecture notes are, and so it's up to 5 extra credit points for Math 115 final, up to 5 extra credit points on the Math 125 final for every section. And so it could be 5 points that for each section. That's one whole grade. That that's a lot. It's unheard of. Do we get a response? Uh, Not usually. No, because I usually try to collect. I try to do them all when they're done. If you ask me, after you've done it, if I've gotten it, I'll respond. But I usually don't respond when I get the each of these. Any other questions? Okay. There are no other questions. Then I guess that's it for today. Okay. So I will start to um, remove participants so that people can see these lectures. Okay. Oh, let me see. Where is that?